Hi, this is Dr. Goldstein, and I'm going to show you an example of a classic optimization problem. Now, it's important to note that optimization problems are a very basic kind of example of how calculus can be applied to real-world problems. So let's say that I have 50 feet of fence, and I want to enclose two identical rectangular gardens. I specify that the enclosures should share an edge, as you can see in the diagram that I've drawn on the page. So the question is, how can I do this and have the largest possible area for my gardens? So working from the given information, I know that the width of both of my rectangles is the same. So I'm going to give them a variable, and they'll have the same name as each other. So this side length here is x, and this side length here is also x. And then the height of these rectangles could be something else, so I'll give that another name, y. And so in total, I have let's count them. 1, 2, 3, 4 sides of length x, and I have 3 sides, 1, 2, 3 sides of length y. So if I want to consider how much fence I will need to build this enclosure, we know that we need 4x plus 3y feet of fence. And the fact that I have 50 feet of fence available means that I get an equation 4x plus 3y equals 50. Now this is what's referred to as a constraint equation, because it is the constraint that is given within the problem. Okay, now we actually address the part of the problem where I'm asked to do something. I want to know, how can I build this with the largest possible area? So I am asked to maximize the total area of my garden. And since my garden is rectangular in shape, I know that the area is going to be length times width. So I know one side is y, let's call that the length, and then the other side of my shape, if I take this entire edge, that entire edge is 2 times x. So all in all, the area of my gardens is given by 2 times x times y. And this is what's called my objective equation, or my objective function. Because it's what the objective of the problem is. I want to maximize this quantity. So it's important to note that I know exactly how much fence I have. I have 50 feet of fence. And so that quantity, this length of fence, goes into the constraint equation. On the other hand, I don't know how much area I'm going to end up with. That's the quantity that I need to maximize. So that's the quantity that goes into the objective function. Okay, having established this, we have our constraint, which is 3y plus 4x equals 50, and we want to maximize our area, which is 2 times x times y. Now what I'm going to do is take the constraint equation and solve for one variable. And I could do either one. I've decided that I want to solve for y. So I'm going to subtract 4x from both sides, and I have 3y is 50 minus 4x, and I divide both sides by 3, and I get that y is 50 minus 4x divided by 3. And now what I'm going to do is I'm going to take that and I'm going to stick it into my area function. So instead of 2 times x times y, I can write 2 times x times 50 minus 4x divided by 3. And so my area function becomes 100x minus 8x squared divided by 3. And if I want to make that look a little bit less scary, I can write that as 100 x minus 8 x squared. And now that's just a plain old polynomial. So what I've done here is I've taken my constraint equation and I've used it to replace a variable in my objective function. And so now I have a function of 1 variable. So we use the constraint to replace a variable and get a function of 1 variable, which in this case is x. It doesn't have to be x. Sometimes we use different letters. But now the point of this is that we want to maximize area. And now I have area in terms of 1 variable. I want to maximize a of x. This I can use calculus. So now we can use calculus. Okay, so let's do that. We have a of x, and we want to find its maximum. We want to find its largest value. So in order to do that, we take the derivative. So the derivative a prime of x is going to be 100 thirds minus 16 thirds x. And if I want to find the maximum, I want to look for critical points, and that's where the derivative is equal to 0. So I set this equal to 0, and I solve. I have 100 thirds is equal to 16 thirds x. I can multiply both sides of my equation by 3 over 16. And those 3's cancel out nicely. And so what we get is that x has to be 100 over 16. And if I want to be a good mathematician, I reduce that to 25 over 4. And if I want to be understandable, I write that as a decimal. I write that as 6.25. And so what we've found is that the variable x that we reduced our original equation to, our variable x wants to be 6.25. Apparently. Remember, we wanted to find a global maximum. So in order to check that I have a maximum, I can use the second derivative test. And in this example, this is the easiest way to do this. My first derivative is 100 thirds minus 16 thirds x. And so the derivative of that is just minus 16 thirds. And so at x equals 6.25, I know that a double prime of 6.25, well, this is just negative 16 thirds. This is less than 0. So I know that a of x is concave down, which tells me that x equals 6.25 is a maximum. Now, it tells me that it's a local maximum, but because it's the only one, I know that it has to be a global maximum because my function can't turn around. This is the biggest that this function can get. Okay, so I've found my x value where I have a maximum, but if you went back to someone who asked you this question of, how big should my gardens be? And you said, oh, well, x has to be 6.25, they'd look at you and say, what? What do you mean? So we have to go back to our original problem, and we have to translate. So now I know that x has to be 6.25. Remember, we had this diagram where we had these two rectangles where the base was x and the height was y, and we need to know now what is y. So recall we had our constraint equation, which was 3y plus 4x is equal to 50, and we actually solved that for y on a previous slide. We have that y is 50 minus 4x divided by 3. So we know that when x is 6.25, y is going to be 50 minus 4 times 6.25 divided by 3. And when I plug that into a calculator, I get 8.3 repeating. So now I can go back to this person who's asked me a question and said, oh, well, x has to be 6.25 and y has to be 8.3 repeating. And they're still going to look at me like, what? What are you talking about? So what I really want to do is write my answer in very plain, understandable English. And so what we say is that we make 2 pens of dimensions 6.25 by 8.3 repeating feet, and they're joined along the side corresponding to y, which was 8.3 repeating. So they're joined along the longer side. And now someone could take this information, someone could take these dimensions and how to attach the pens, our 2 fenced gardens, and they could actually build this thing. Okay, so one thing that we could do in order to check our work if we wanted to, let's say that we're taking an exam and we want to make sure that we didn't make some silly mistake, you can check that when you actually have lengths of these sides of these lengths, so 6.25, 6.25, and then these 3 sides of 8.3 repeating, you can check that these all add up to 50. And they do. I plugged that into a calculator. Take my word for it. So that is a nice way to check your work at the end of these really long problems to make sure that you haven't just made some computational mistake. Okay, so here is this whole process summarized. So this is what's called an optimization with constraint problem. We're trying to optimize something, either find a maximum, sometimes we want to find a minimum, and we're given some sort of constraint in a problem. In this problem, we wanted to maximize the area, and the constraint that we were given is a limited amount of fence. So the first step in these problems is always to diagram the given information and identify what it is that the unknown quantity is. So in this case, the given information went into our constraint equation, and the unknown quantity of the area went into our objective function. Once you have your diagram and you've figured out what you're given and what you want to find, you want to pick variables and then turn that information into the explicit equations. You want to write down your constraint equation and you want to write down your objective function. The next step is to do this variable replacement. So we solve the constraint equation for one variable and plug that into the objective function, so that what we're left with is a function of one variable that we can then use calculus to find the global min or max. Now the last step of this problem is actually doing that calculus, finding our answer, and then translating it back to the original setting. And throughout this entire process, you always want to think about the answers that you're getting. So don't forget to think. So for example, if we had gotten a negative quantity in our problem, we would have said, I think I made a mistake because we were dealing with lengths of fences, and you're not going to have a negative length of a fence. So throughout this entire process, remember, you are dealing with a problem that comes from the real world, and so you should get answers that make sense in the real world.